All right, welcome again. We are going to talk about introduction to hypotheses testing. We're going to be identifying significant results with probability that the rare event rule for inferential statistics. So if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what is typically expected with that assumption, we conclude that the assumption is probably not correct, even though that we've done a testing. So we're going to do another example. So we have assumed that the population of human body temperatures has a mean, it's already telling us it has a mean of 98.1. And as it's commonly believed, so this is the mean already. We also assume that the population standard deviation, so sigma, is 0.62 Fahrenheit. Based on the data set 5, the body temperatures in Appendix B, we know that the sample size N is 106 of randomly selected, and the mean of the body temperature is 98. So we're given a sample mean of 98.2 was obtained. If the mean body was really 98.6, find the probability of getting a sample mean of 98.2 or lower for a sample size of N of 106. So based on the result, 98.2 is significantly low. What does this result about common belief that the body temperature is 98.6 Fahrenheit? So we begin by identifying that this example, it's not saying that it's normally distributed, but we know that N is equal to 106, which is greater than 30. So that condition is satisfied. So we're able to use the Z is equal to X bar minus mu over sigma. However, because we're asked for a particular sample size, we're going to use sigma now to be equal to sigma over the square root of N. We're going to have to find the actual value for more than one. Okay. So we know that the mu of X is equal to 98.6. That's the first thing that we highlighted in our problem. We know sigma of X will be sigma over the square root of N. We know that sigma is 0.62 and that N is 106. So then there is our mu and there is our sigma of X. So we need to know, well, what's X bar? X bar is what we found from the sample, 98.2. So they're asking us to look at, find the probability, let's highlight that. We want to find the probability of a sample size of a mean or lower. So when we graph our standard, our density curve, we're going to put in 98.2 Fahrenheit or lower. So we want to find something cumulative from the left. So we're going to be using our table A-2. So we're going to go ahead and find our z-score. We're going to substitute X bar minus mu of X divided by sigma of X. So we found that sigma of X was equal to 0.62 divided by the square root of 106. So you want to do that first. So let's punch that in our calculator to verify. Okay. And we get negative 6.64. What does that mean? This is a credit, sorry, this is a credit score. This is a z-score of a negative 6.64, which is, again, the area under a curve, which is very close to 0. So what does that mean? Because the area is up to negative 3.5, we know that the shaded region is very close to 0.001. That interpretation says, so if we go to our table of z-score values, it goes all the way to negative 3.50. It doesn't go any further. It's not negative 6 point something. So see how this one's 0.0001? That is the lowest it could be before being 0. So then what does that mean? What is the interpretation of this mean? The result shows that if the mean of our body temperature is actually 98.6, we assume that there is a very extreme small probability of getting a sample mean of 98.2 for 106 subjects, when 106 subjects are being randomly selected. Okay. So the University of Maryland researchers did obtain a sample mean, and after confirming that the sample is sound, there are two feasible explanations. So one of the explanations is that the population mean really is 98.6, and the sample represents a chance of a rare event. So we had this 98.2 was extremely rare because the probability we found it was 0.0001, very unlikely, or that the population mean is actually lower than what we assume of 98.6. Okay, so this example is very typical because the probability is so low, and we have a more reasonable thing to say to conclude that the population mean is lower than 98.6. Okay. So when in reality, our temperature is closer to 98.2. Honestly, I don't know for the rest of you, but normally my temperature is like low. I'm like cold all the time. I'm not sure why. I have hypothermia, not hyper, not hyper, but hypo, so less than the normal. Okay, so we'll finish this last one by doing an example or talking about what is a correction for a finite population. When we're sampling without replacement, this is what we saw at the end of section 6.3. When we see something or a sample without replacement, then the sample size of n is greater than 5% of the finite population of size n. So we have to do a corrector. So there exists this finite population corrector of sigma of x, which is big N, which has n is the population size, and little n is the sample size. This is in case if they were asking for a correction, then this is what you'll use. Normally on your homework, we were not going to be asked to do that. But in case they did, you would just use this formula. You would use this, you would multiply this finite corrector to sigma of x to get something more accurate if this would be needed. And that is the end of 6.4. Okay, so we saw some examples of applications of a standard normal. We talked about the central limit theorem and being able to do everything from a central limit theorem and going back to z-scores and table A-2. For 6.5, we're going to be assessing normality. So we want to show whether something is normal or not normal. So in the following chapter is important for us to look at what makes something normal. What are the conditions? So how do we make from a population having a distribution that is approximately normal? In this section, we will present the steps for determining whether a sample data satisfies the requirement for a normal distribution. The first thing we need to do is actually we're going to be constructing a histogram and determine whether this is a roughly bell shape, or we are also going to be constructing a normal quantile plot that uses criteria given later in the section. So a normal quantile plot, we could do two things. We can have them as little list. And remember how we had like these graphs that look like this as pieces like dots? Or as box plots, okay? So a normal quantile plot or a normal probability plot is the graph of points x and y where each x value from the original set of sample data and each y value corresponds to a z-score is expected from the standard normal distribution, okay? We are going to be constructing a histogram. Remember what a histogram was? We have here different lists where on this side, we have the class width. And then over here, we have the frequency. Hopefully, if you haven't forgot on how to do a histogram, this was a frequency histogram. We have different types of histograms, and it has to mimic a bell shape to conclude that it does have a normal distribution or something approximately normal. We also have a normal quantile plot. If a histogram is basically symmetric and the number of outliers are 0 and 1, we can also use Excel or XLStat to generate a normal quantile plot in Excel. We don't need to do that. Another way that we can do this is using StatDisk. If you want to use a technology, we can plot this and then they could do that for us. So what is the procedure? The procedure for determining whether it is a reasonable to assume that a sample data will be having a normal distribution is that the population distribution is a normal if the pattern of the points is reasonably close to a straight line and the points do not show some systematic that is not a straight line pattern. That will be a normal distribution when something follows a line that's increasing or shows some patterns. What will not be a normal? Not normal will be a population distributions with one of these conditions. The points do not lie in a reasonable close to a straight line, or the plots show some systematic pattern that is not a straight line pattern. Maybe it can be a parabolic. Maybe it looks like a U. It looks like an exponential, something that does not look like a straight line. It must have a straight line to have a normal distribution. Okay. Another way to distinguish whether something is a normal distribution, there are more advanced procedures for assessing normality. They're the Ryan-Joyner test, Shapiro-Wilk test, Diagnostio-Pearson, the chi-square goodness of fit test. We're not going to be talking about that. This is more advanced methods that we use. We will be using chi-squared goodness of fit, but that's more of chapter 10, the end of chapter 10, so we still don't know that yet. So what are some examples? Look at the graph. So this is a histogram. This is a frequency histogram. That looks normal, does it not? It follows this bell shape. And also this is normal because it's a systematic pattern. Represented by a straight line. Okay. So that is a normal example. There is also a uniform example that looks like this. This is a histogram, but notice how they're all about the same probability. This is a histogram with a uniform distribution. We saw that example already. Okay. And then look over here. Look at the systematic pattern, but look at this. Notice that it has some curvature. This is not normal. It does not follow a straight line. We also have a skewed. So notice how this starts really high. This is like super skewed. This one's skewed to the right. And look at this. Look how this does not follow a straight line either. This is skewed to the right, not bell-shaped. So this is not normal, it's skewed. Now, if we want to construct manually the construction of normal quantile plots, we begin by sorting the data by arranging the values in order from lowest to highest. And then we want a sample size of n. Each of the value represents a portion, 1 over n samples. So using the known sample size, we're going to do 1 over 2n, 3 over 2n, 5 over 2n, so on and so forth. So these are just odd numbers that we have up top that we can split and then convert this to different cumulative areas to the left. So we're going to do some examples. We're not going to do them manually, actually. We're going to use the standard normal distribution software or table A-2 to find the z-scores corresponding to the cumulative area. So for us, we're going to probably be using StatDisk for us for normal quantile plots. So let's look at an example. Let's see. A normal quantile plot for us, if we were given a particular data, let's look at the first one. It's saying part 1. I'm not looking at part 1. Let's find what the example are talking about. I think it's this one, but I can't really tell what the scores are. So it doesn't, on your homework, does it ask for the normal quantile plots? This is what they're doing. I'm going to give you some data. So I don't have the data set values. Let me look for it. Let me look at my downloads. Desktop. So this is section 6.5. I'm looking at the notes. And I don't see it. It should give me all of the values here. All 1,000 Dallas to compute times. So on your homework, let me share a StatDisk. So in case they ask for it, I'm not sure it does because on your homework I didn't put one for quantile plots, but in the case that it does show, let me go to StatDisk so then you're able to do it. So on StatDisk, you're going to be able to put the data. So when you're assigned a homework problem that it's asking for a normal quantile plot, it's going to be a set of data points, maybe 30 points, maybe 50, maybe 100. You can just copy and put to clipboard or copy to clipboard, and then you could just literally paste it here. Once you paste it, so I'm just going to do an example, like 1, 2, I'm going to make it up. Let's say I have different values. 14, so on and so forth. Oh, not E. 42, 32. I'm making numbers up. 12, 13. I don't know. Whatever it might be. I'm just, again, punching in some numbers. And then I'm going to tell it my value. So data, do you see there's this normal quantile plot? And then you're going to select column 1. It's going to ask for the X values, you see? So this is my quantile plot for my first column. If I want to do my second column, there it is. So you can put in the values for the X and for the Y. So this is for the X. If I go for my second one, and that's going to be now the other y values. Oh, let me change this. Can I change this to y? I guess it's only my x. So there's my sample editor. And I'm gonna use my first column, go to data, normal quantile plot. You're gonna be selecting column 1, normal quantile, and then there it is. You can see that this does not follow a straight line, so this would not be normal. So that way you're able to actually graph and see it. So you guys can play around with that. But I don't think that you're asked anything about the normal quantile plots. If they do, please let me know. So see how they have it? See, this is what we have. So here my data is not showing up, but look at this. The computer will do it really fast. N is 1000, so I'll have 1,000 of these. Okay. So then you're going to do a histogram. You can also do a histogram, by the way, on StatDisk. So again, data, you can hit histogram. You can put a title and then it will do it for you. So the same way you click on data and then you hit histogram. So you don't even have to do it by hand. You can just literally do it on StatDisk. And that's what I suggest you to do. For these few slides, we talked about outliers, the definition of what that is. We should always be aware of the presence of any outliers, something that will drastically change your results. Test for effects of outliers by applying statistical methods for these. And then the second time with outliers excluded. So what happens when you remove the outliers? Is it now normal? So sometimes you're going to be able to discard outliers only if they're identified as errors. Otherwise, they will remain. Okay, so Dustin, thank you for letting me know. So Dustin is saying that you're asked for histograms and normal quantile plots, but the data was given. So you can literally, again, you just copy and paste the data, and then you're able to just submit that on StatDisk, and then you can see whether it's normal or not normal. Does that help everyone? I just want to make sure that we're covered for that. Okay. Thank you, Dustin. So many, and then just the last few. So the data transformation, many data sets have distributions that it's not normal. So not everything will be normal, but we can transform the data or modify the data so then we can have a normal distribution. One common transformation is by taking the value of x and taking its logarithm. These are just additional things you can do. We're not going to be doing that right now. So if a distribution of the logarithms is a normal, then the distribution of the original is called a log normal distribution. We're not going to go that far. Don't worry about that. These are just ways that when you are in higher statistics, that's what they do. And they also use programming or R language to do more statistics in a really faster way. All right, the last section that we will do, we have 30 minutes and we're probably able to finish. Normal as approximation to a binomial probability. So remember that we saw a binomial probability. If we remember, what is a binomial probability? How did we calculate a binomial? Who remembers? Do you remember? So we had this formula, n factorial, n minus x factorial, p over n minus x, and then q. I think it was p over, where is it? So the binomial probability was when we had the combination and then p raised to the x and then q raised to the n minus x. So we are going to have something that's going to be approximately to a binomial, not necessarily. So a normal as an approximation to a binomial. And the way to do that is, in this section, we'll be presenting a method for using a normal distribution as an approximation to the binomial distribution. Given probabilities P and Q, right? We talked about P, we talked about Q, where Q is 1 minus P and the sample size of n, and then we need to satisfy the conditions that n times P is greater than 5, n times Q is greater than 5, are both satisfied, and that the probabilities from a binomial distribution can be approximated reasonably well by using a normal distribution having these parameters. So now look at the mean. The mean can be found by multiplying n times P, the sample size of n multiplied by the probability P, and sigma as the square root of n times P times Q. How can we approximate? Well, the binomial probability is a discrete with whole numbers as random variables of x. But as a normal distribution or a normal approximation, we have a continuous variable. So to compensate, we're going to use a continuity correction with a whole number. So if it's not a whole number, we're going to do either x minus 0.5 or x plus 0.5 to adjust. So we want to make sure we are representing it by a whole number, and it's going to be averaged between x minus 0.5 and x plus 0.5. Okay. So in a previous section, we saw the binomial probability distribution has a fixed number of trials, which was n. The trials are independent. Trials are each classified into a success and a failure, and trials with the property that the probability of successes remains constant. This is the notation. The fixed number of trials is n. The number of successes, the specific number of successes is x. P is the probability of successes. Q is the probability of failure, or 1 minus P. Okay, we saw this already back in chapter 5. There is a rationale for using a normal approximation. So in the past sections, we've been looking at normal distributions, standard normal, uniform distributions, how can a sampling distribution, we've seen all of it today. So what we're trying to do is we're going to use a sampling distribution from a sample proportion that tends to something that is approximately normal. So we also see the following probability in the histogram. So this is our n value. This is our P. And it's saying that in Mendel's famous hybridization experiment, he expects 25% of his 580 peas to be yellow, but he got 152 yellow peas at a rate of 26.2%. The bell shape suggests that this that we can use an approximately normal to approximate the binomial. So look at this. When they graphed it, when we see this histogram, this is a bell shape. So this exactly qualifies to be a candidate for a normal distribution, even though it's actually a binomial. So because we know the successes and the failures, let's go ahead and write them down. We know that n is 580. We know that P is 0.25. We know Q is what? 0.75 because it's 1 minus P. And then what else? The number of successes. So the number of successes are found by what? We have the following. The sample size is a simple random sample. So we are now going to be using a standard normal, a normal distribution to find the solution for this problem. The sample size is a simple random sample. We have the number of successes of P, the proportion. We have N, they're independent trials for a binomial probability. So we first need to satisfy the conditions. N times P, is that greater than 5? N times Q is greater than 5. Well, remember, this is, I think, 508. Oh, 580, sorry. So we need to multiply 580 times 0.25. Is that greater than or equal to 5? Yes. Is 580 times 0.75 greater than or equal to 5? Yes. So both of the requirements suffice. So if the above requirements are satisfied, then the probability distribution of a random variable can be approximated. So to find the mean, we need to know n times p. So n is 580, sorry. So mu is going to be 580 times 0.25. Let's find what that is. So 0.25 times 580 is 145. That's going to be the mean. And the standard deviation will be the square root of 580 times 0.25 times 0.75. So let's do that. 0.25 times 0.75 times 580. It's going to be 108.75. So I'm going to do the square root of this. Oops. Which is equal to 10.42 or 43 if I want to approximate to 2 decimal places. Now, when we're using a normal approximation, we need to adjust the discrete whole number by using a continuity correction. So in this case, we didn't really have to do x plus 5. So we found a mu to be 145, and we found sigma to be 1042. Okay. So if we do this, we want the probability that at least 152 yellow peas. So the discrete whole number is relevant. So x is the number of successes. We use the continuity correction to represent the value of 152. So we need to do 152 minus 0.5, 152 plus 0.5. That is applying the continuity correction. So we have the value 151.5 and 152.5. Okay. So this one's saying representing 152 or more. So that means we're shading to the right. We are going to find the area under the curve. It's already telling us what it is. But we're going to be using z-score. Okay, we need to find what the z-score is. So to find the z-score, we can use table A-2. We knew that x by using so remember we have two different ones. The correction continuity one, which is 151.5 and 152.5. So we're going to look at both of them. So when we're finding the z-score, 151.5 minus the mean over sigma, we get 0.62. When we look at the area to the left, cumulative from the left is 0.7324. However, we want the shaded region from the right. Look over here. We want the shaded region from the right. Do you see this continuity corrector thing that I was talking about? 151, 152. So we're looking at this area right now. So we have 0.2665 when we subtract 1 from the cumulative distribution from the left. Okay. So we took the smaller one. So the interpretation is that Mendel's result of 152 is greater than 145. So he expected with his theory of hybrids, but P of 151 or more is, look at this, 0.6265. So that's not significantly high. Look at the percent, 26%. Okay. So in reality, this experiment does not contradict Mendel. So he's not wrong. So look at the continuity correction. When we use a normal distribution, we find a continuity correction that is being made because we're changing from, let me explain why do we do that. We are changing from a binomial probability, which is a success to a failure. It's a discrete value, to a continuous, something that's continuous. So we have to take into consideration that interval of x minus 0.5 and x plus 0.5. So now we look at what happens in between of 1.51 and 1.52, okay? Because we wanted 152 or more, we use the area to the right of 151.5, okay? So here, these are more uses of the same business. So we're gonna do the same thing for now the exact 100. So on the other one, it was 152 or more. See, that's why we shaded the other half, this side. 152 or more. So we looked at 151.5 and we shaded to the right of that. Now, on the next part, they're being more specific because they're saying exactly. So if we're looking at a probability of exactly 152 yellow peas, for that one, we're going to use the same mean of 145 and sigma, but now the region is going to be exactly right here, this little piece. It's actually the exact. We don't want to know what happened to the left, to the right. We want to know exactly at 152. So we need to find two different areas. The area cumulative for 151 and 152. So we're going to have to do this problem again that we did. So it was 151.5 minus 145 over sigma, which was 10.4283. And we did that one already. That one, we found a z-score for that. And we have 152.5 minus 145 over 10.4283. So we're going to have two different z-scores. So this z-score was 0.62. This z-score is 0.72. Now, when we go and look at the cumulative areas from the left, we're going to have 0.7642 minus 0.7324, which is 0.0318. So the probability of having exactly 152 P's is 0.03. So basically, I'm finding the area in between these two, in between 151 and 152. And I'm looking at the z-scores. So the z-scores, based on the calculations, were 0.62 and 0.72. So if I go to my table, so I'm going to go over here at my table. So I said 0.62, 0.62, so 0, 1, and 2, there it is. 0.7324, and then 0.72, which is this one, 0.642. So I just subtract these two. Okay, just showing you how I did each step. Okay. So this interpretation says, in an earlier section, we saw that X successes among N trials is significantly high. If the probabilities of X or more successes is unlikely. But we saw that Mendel's result for 152 contradicts his theory, right? We saw 26% when we did it through a normal. So when he did it through using a binomial probability, he got 25%. But then we saw through a normal probability that if I want to find exactly 152 p's, the probability is 0.03, which is not a relative probability, okay? The probability that is relevant for us was the 26%. First, on the first example, it was 152 or more. You can't really have the exact one, okay? So we can say that the relevant result is getting at least is as extreme as the one obtained. So extreme value was this 0.035 because we were looking at the exact amount of yellow peas on his experiment. Okay. You can also do this through technology. We can use this using StatDisk. For the first example, again, we would have to be given some values for that. Again, let me just show you really quick on how would you do that through StatDisk. Let me open that website. So let me share my screen now. You're looking at StatDisk. So we're asked to do a binomial probability. So here we have sample size probability distribution. There it is. So we have a binomial distribution, Poisson, a normal distribution here for particular z values. So if you know what the z-score value is and you're looking for the cumulative area from the left, you can get the answer really quick. You can look at the binomial distributions, and this is where you would actually select the data. Looking at the successes. So all you really need is the number of trials of n and the probability and the number of successes. So there's a probability p, the trials of n, and the x values of the successes. That's all you need, really. So then you can always use technology to find the solution as well. So see, this is an example. You can put, this is using StatCrunch, I believe. So it's either a StatCrunch or a StatDisk, whichever one. And it also tells you the mean, the standard deviation for a few. So this is good. It always does it for a P of X. So this is the exact P or fewer, the probability of P or fewer or P or greater. Okay. So you will always have that available when you plug in the X and Y values. All right. If there is not any more questions, that is the end of 6.6. So I will stop the recording now.